Greetings everyone, we will continue our discussion on information retrieval systems. In the previous session, we have started about paired trees and we have discussed basics of your paired arrays. In this session, we will be looking about the paired tree representation as paired arrays and how that particular paired arrays will be stored in your memory and various implications of that particular storage. So, we will be looking about paired arrays. So, in the last session, we have started the paired arrays. So, what is paired array? So whenever you are having a search in your one of the buckets which in your paired trees, so I told you about this bucketing concepts in the paired trees where you instead of storing the complete array, that is instead of storing the complete subtree, we will be storing a set of external nodes in your memory as bucket. Okay, all the external nodes which are part of bucket will be present in a sequential manner. So we have to search all the, whenever a search comes into this bucket, we have to search all the particular external nodes to find out the result of the search. So when a search reaches a bucket, we have to scan all the external nodes in the bucket to determine which, if it satisfies the search or not. So we have told you about this particular bucketing principle where we will be, instead of storing each and every internal node present in the tree, we will be storing a part of this subtree and the external nodes which are present in the subtree in one bucket. When a search reaches one bucket, so we have to compare each and every external node present in the bucket. There will be no association between any of these buckets. We have to compare all the buckets in the bucket, all the external nodes in the bucket and find out whether the search is successful or not. Okay, so when you are performing this thing, if the bucket is too large, then cost become prohibitive. So if you are having a smaller bucket size, then it will be a better searching probability. If you, as the size of the bucket increases, your particular search also will become very complex. That is, the number of comparisons you have to perform while searching will increase drastically. So it is not significant for small buckets. Whenever you are searching for this thing, it will not be significant if your bucket size is very small and the number of external nodes that are present in your bucket is very small. As the bucket size increases and the number of external nodes present in the bucket increases, okay, the costs also will become very high. So instead of solving this thing, so how you are going to get this arrays? So this is simply to let the bucket grow well beyond the normal bucket sizes, including the option of letting it to be equal to n, that is, the whole index degenerates into a single array of external nodes ordered lexicographically by systrix. Okay, if you are having your external nodes, you will be usually making your bucket size as smaller values. When you make your bucket size as 2, okay, you can store a part of the node. You can store a part of the node as a bucket and a part of the subtree as another bucket. Okay, a part of subtree as one bucket. So when you are having your bucket size as small, you will not be having too many issues. What you do is you grow your bucket size very large. That is, now if you are having bucket size 2, this particular subtree is having 2 external nodes. So I can store this as one bucket. This subtree is having 2 external nodes. I can store this as one bucket. And now you will be having 2 buckets and 1 external node. Okay, this will not be having any issue. But if you store or if you increase your bucket size to a larger value, now if you increase your bucket size to a 5, now the complete tree can be treated as one subtree and you can store the complete set of nodes in one bucket. So what you are trying to do is we try to grow the bucket size well beyond the normal bucket size levels. Okay, so we initially started a smaller number and we grow the bucket size well beyond the normal numbers and we let it reach your n value. That is, your n value is the number of external nodes that are present in your complete tree. Okay, so we will try to reach it to n, that is when your bucket size is equal to n. When your bucket size is equal to n, then all the buckets, that a particular bucket contains all the external nodes. So these external nodes will be present lexicographically in a sorted order, that is they will be present as 1, 2, 3, 4, 5. Okay, not by their numbers, by their contents of the sysstrings. So whatever the sysstring that is present here, so we have to take all the sysstrings and the lexicographical order of those sysstrings, and they will be present in the lexicographical order of the complete external nodes. Okay, so we keep the bucket sizes small at the initial levels, and we grow the bucket size to larger levels until we reach n. So when I reach your bucket size as n, then all the external nodes will be present in one bucket. At that time, we will be getting all the external nodes or sysstrings in a lexicographical order in an array. This array we will be calling it as the pat array. Okay. This array we will be calling it as the pat array. So along with this, you can also implement the pat array in this manner. Keep the external nodes whatever that are present in a bucket in a relatively same order as they would be in the tree. So you can also create the pat tree in this manner, where you keep the external nodes in the same relative order that are present as in the tree. So 7 is present as the first external node, so we place it as the first external node here. So 4 is present as second external node. So in the similar relative order in which they are present, we will be storing them in your pat arrays. So that is we take the pat tree. From that pat tree we store all the external nodes in one array. That array we will be calling it as pat array. So all the information that is present in your pat trees will be present in your pat array. Along with the pat tree will be having the pat array, which will be giving you more options to perform. So the second option regarding your pat arrays is searching pat trees as arrays. That is, you are having your searching algorithms. I already told you all the searching algorithms related to pat trees. Whether you can implement all those searching algorithms by using pat arrays. Okay. So prefix searching and range searching can be implemented with better time complexity by performing an indirect binary search over your array. So you can use your pat arrays and perform your prefix searching and range searching with better time complexity than what you have done before by using pat trees. Okay, your pat arrays will be helpful to perform these two searching techniques better than your pat arrays. Better than your pat trees, by performing the binary search over your tree. Okay, so this is the first thing regarding your searching in your pat arrays. The second thing is the most frequent searching can also be implemented and it can be improved. Okay, the most frequent searching method that also can be implemented and you can get the better results, but it will be very complex to implement by using pat arrays, and this discussion is beyond implementation of this thing. Okay, the last one is the longest repetition sequence search can also be improved, but with additional data structures. So this searching technique also can be implemented, that is, this application or searching method also can be implemented and improved, but it will need additional data structures more than whatever you are having here. That is, along with pat array you need another data structures to implement this longest repetition search, and it can improve the time complexity as well. But overall you can see that the prefixing and range search method can be implemented directly by using your pat arrays, and you can get better time complexities more than what you get from your pat trees. Okay, so you have to remember that prefix searching and range searching will be having better time complexities by using your pat arrays. Okay. So building your pat trees as arrays, that is how you can build these arrays and how you are going to store them in memories. You already seen how you are going to store your pat trees in memories. Okay, how you have to place the trees one by one, how you have to place them on your disk files, how you will be storing them, with some links. Okay, we have seen all those things, how you are going to build pad trees as trees in memory. Now how you are going to build the same pad trees as arrays in the memory. So first we will present the building operations which can be done effectively. Then two of the most prominent algorithms for large index building, how you can build large indexes. We will be looking about those things. First we will be looking about how to build these pad arrays. Then we will be looking about how to build pad arrays for the larger indexes. Okay. So first thing, if a portion of this text is small enough to fit in a main memory, okay, whatever the text you are having. So remember, you will be having the text and your pad array. So the initial text and the pad array will be present. If a portion of the text, and whatever your text you are having, if a portion of this text is small enough to be fit in the main memory along with its pad array, then this process can be done very efficiently as it is equivalent to string sort. Okay, if you are having your string, if you are having your text and your array, so this particular text fragments, if you are breaking down the text into fragments, and there will be subsequent, if you are breaking down the text into T1, T2, T3, okay, these are the fragments, and we will be having corresponding pad arrays PA1, PA2, PA3. And if these fragments, that is TA1 and PA1, both these fragments can be fitted into the main memory. Okay, if this particular two parts can be fitted into the main memory, then it can be done very efficiently. That is, you can fit them in the main memory and perform applications very easy. Okay, that will be one part. If paging is used to simulate a larger memory, then random access patterns over the text will certainly cause several memory thrashing. Okay, if whatever you are having, that is the text and array, has to be implemented by your virtual memory, and it has to involve, okay, a larger memory, and you have to implement the paging process. At that time, the random access, what you have to do in your paging process, and the paging process itself will take lots amount of time, and it will take lots amount of memory thrashing to perform this index. So when you are building indexes by using pad arrays, remember that they have to be small enough, and if they are small enough, you have to be, if it is a larger file, or if you are having larger text and larger index, you should be able to break down that index into parts, okay, and you should be able to place that particular parts in the main memory directly. If you are able to place those parts in the main memory directly, you can implement your pad trees as arrays very easy. Okay, so if you are having larger memory and whatever your particular text and array can be fitted into the main memory easily, then also it will be very easy to and efficiently it can be implemented. So how you are going to implement? That is, you are having one thing where you will be having smaller parts, that is, these parts can be fitted into the main memory, and you are having another thing where you will be having larger texts and arrays where it cannot be fitted into the main memory. That is, the parts cannot be fit into the main memory. So you will be having two different algorithms, one for your parts fitting, that is where the parts can be fitted into the main memory, and another one where you can't fit them in the main memory. So Quicksort is an appropriate algorithm for this building phase, since it has almost sequential pattern of access over your sorted file. For maximum reveals, we can put all of the index array on the external storage and apply Quicksort indirectly over the text. Okay, either you can place a part of the file in the main memory and perform Quicksort to get your particular index, or you can implement an indirect Quicksort where you are not breaking down and placing the complete file in the main memory. Sorry, we are going to place the complete file in the external storage and apply the external Quicksort, okay, over the text, so that you will be getting your index complete. Okay, you can perform any of this thing, that is, you have to perform the Quicksort so that you will be getting the better building phase of your index. Okay, you can create the index much better, and either you can perform the internal sort of your Quicksort, by breaking down them and storing them in your main memory, or you can perform the external sort, okay, and perform the external quicksort over the text by storing them in the external memory. You can perform any of these two options. So this is the algorithm of choice for small files where you are going to break down, where you are having a file which can be fit into the main memory. So this is the algorithm of choice for small files and also a building block for other algorithms. So you can use the same whatever you are doing and implement for other algorithms. What is this algorithm? The second case that can be solved efficiently is the case of merging two indices when the text plus twice the index of one of them fits in the main memory. As I told you, it can be implemented and efficiently by having or merging two indices when the text and the index fits in the main memory. Okay, so this part can be better understood if you see the implementation. So the text of the small file together with the part array for the small file plus an integer array are kept in the main memory. So three parts are kept in the main memory. One is your part of the text which you are trying to index, and the part index, that is your part array, whatever you want to implement, the part array will be present in the main memory. Apart from that, we will be having the counters. The counters count the number of strings that are present in between these arrays. So what is the thing is the integer array, that is this is the integer array what you are using, is used to count how many strings of the big file fall between each pair of index points in the small file. Okay, what you are trying to do here. So to have a quick understanding, this is the complete process what you are doing for your part arrays. So initially you will be having a large index. For this large index, you have to create smaller indices. Okay, what you have to do is you have to take one complete text. For the text, you have to create the large index. Okay, now break down the text into parts. For those parts, you create the small index. Okay, and for this small index, you have to create the counters. That is, if this is the small index, this particular small index contains 8 entries, and this small index will contain 3 entries, this small index will contain 12 entries, so on. You are going to break down the complete large index into small indices like this. And from that you are going to create one additional index which will be having pointers to these indices. Okay, so where you are having, this will be the third entry, next to 12 entries, this will be next 12, next 3, next 8. So this will be the new index what you are trying to fit. So when I am trying to search for some certain item, so whether my item is present within this range. Okay, I will check whether my item is present in this range. If my item is present in this range, I will go to the corresponding small index. Okay, so what you are trying to do is, this will be the main index what you are going to create. This will be like a pointers to this index. Okay, this will be, the new index will be like a pointer to the smaller indices, and each index what you are trying to do here. So when I try to search for a particular item, so that particular item will be present in one of the range. Okay, you have to do the sequential search of all these ranges. So it will be present in one of the ranges. So if it is present in one of the ranges, I will go to the corresponding small index. Okay, that small index will refer to the larger index where your actual elements will be present. Okay, this is the thing which you are trying to do. So more generally what you can understand is the above approach what you are trying to do. More generally what you can do is, so the general indexing, the general index building algorithm by using the part trees is, first we split the text file into pieces. Okay, the first piece being as large as possible to build an index in main memory. So what you are trying to do is, first you take the complete text, we break the text into pieces. Okay, the first piece should be very large as possible to build an index in main memory. Okay, next The remaining pieces are as large as possible to allow merging via the previous algorithm, where you are going to merge all of them into one new index. Then we build the indices for all these parts and merge each part. Okay, so we are going to break down your complete text into parts and create the indices for those parts and merge those parts to create the larger index. This is what you are trying to do in your part arrays. Okay, so this is how you build your part arrays in the main memory, and this is how you build your part arrays from your part trees. In the next session, we will be looking about new concepts regarding your information retrieval systems, and this will be the conclusion of your part trees and part arrays. Thank you.